Okay. All right. So here is my work. I'll give you guys a minute to check yours. And how'd we do? Okay. I know I heard at least one person on G. How many of you multiplied 16 times 8 to get 128? Is that the best idea?
No. Probably not.
No.
You can keep it split. It made more sense to me that way. On G, couldn't you take out 5 of the 2s? Because there's 7 in the 4th. Under the... Because that's what...
Oh, there. Sorry. There's the rest of it.
Okay.
I was like, surely I did not leave it that way. Yeah. Okay. So remember, most of the time these aren't calculator problems, so we don't want to make our numerical values larger. Keep them smaller. Okay? If you keep them small, it's much easier to work with and simplify in the end. Alrighty. Any questions on any of these? Okay, so let's move on to today's. So we are continuing with 4.2, bless you, and looking at some more properties of radicals. So first term we're looking at is called conjugate. And so a conjugate is basically formed by changing the sign between two terms in a binomial. So again, any binomial. All right, so for example, I could give you the binomial A plus B. And its conjugate is A minus B. So you just keep the first term and then you flip the sign in the middle and you keep the third term.
So that's what a conjugate is.
Mm-hmm. So what if I gave you x cubed minus 4? What would its conjugate be?
X plus 4?
Yes. X cubed plus 4. Okay. And then because we're working with radicals, it has just a slightly more, slightly more specific terminology, specifically a radical conjugate. So as you guys saw in the warm-up, can you take an integer value and add it to a term that has a radical? No, can't do it. All right, so that would be the situation like here, where we had, say, 1 plus the square root of 5. Okay. So then we could say the radical conjugate is 1 minus the square root of 5.
It's the same thing.
It's the same thing. Yeah. It just, we say more specifically, yeah, because there's a radical involved. Or what if I had the fourth root of 7 minus the third root of 3?
Fourth root of 7 plus the radical conjugate.
Exactly. The radical conjugate.
And this is only the radical.
Yes. Fourth root of 7 plus the cube root of 3. Okay. So that's what a conjugate is. And then this next part, adding and subtracting radicals. So just remember, when you have a radical, you almost treat it like a variable, right? Can you add x cubed to x squared?
No.
No, right? The exponents don't match. Even though the bases are the same, the exponents don't match. So it's the same thing with radicals. Both the index of the radical and the radicand have to be exactly the same in order for you to combine them. So that was why, like the example that we just looked at here, right? All we can do is find the radical conjugate with it. We can't combine those two terms together because one's a fourth root and one's a third root. Okay, so yeah.
What is the index?
The index is this term up here.
Oh, in the square root. Sorry, I just didn't know what it was called.
Yeah, so that's the index, and then the radicand is this piece on the inside. Okay, so if I had, say, 4 times the square root of 7 plus 2 times the square root of 7, would we consider those to be like terms?
Yes.
Yes, right? On the square root of 7, they both have the exact same index of 2, and they both have the same radicand of 7. So we can combine them. So this is like, yes, 4 plus 2 is 6. We get 6 square root of 7. Or what if we had a 8 sixth root of 5 minus 3 sixth root of 5? 5 sixth root of 5. Exactly. Indexes are exactly the same. Radicand is exactly the same. 8 minus 3 is 5. So we get 5 sixth root of 5. Yeah. Okay, so we are just going to start tying all of this stuff together. We're going to run through 2, 4, 6, 8 examples, and then I'm going to hang some up on the board for you guys to work together. Okay, so in this first one, all it tells us is to perform the indicated operation and simplify the following. So I look at A, I've got 1 over 5 plus square root of 3, and we're like, well, what kind of operation is there to do? Well, what's the rule we said about?
You can't have a square root on the bottom.
Cannot have a radical in the denominator. So we have to undo that. So what's different now is it's not being multiplied by something. There's a term being added to it. Okay, and so this is where that radical conjugate comes into play. So
I remember doing this.
yes.
Oh. I just didn't know that's what it was called.
Yeah, I just thought you
Okay.
just flipped the sign for some reason.
All right. Yep, so we're going to multiply by the radical conjugate. So this is going to be 5 minus the square root of 3. And whatever you do to the denominator, you have to do to the numerator as well. Okay, and then you just multiply across. I've got 1 times, so nothing changes in the numerator. It's just going to become 5 minus the square root of 3. Now in the denominator, we basically just treat this like we're multiplying 2 binomials, right? So it's like FOILing. Right? I would do 5 times 5 is 25. 5 times negative square root of 3 is minus 5 square root of 3. Square root of 3 times 5 is plus 5 square root of 3. And then square root of 3 times negative square root of 3 becomes negative 3. And then what happens to those two middle terms? They cancel out.
Negative. Oh, because it would be negative square root of 9.
Yes. Yep. Yeah. I'll write that step in. Negative square root of 9. Okay. So again, can't do anything more with the numerator, so it stays 5 minus the square root of 3. And in the denominator, we now have 25 minus square root of 9. So 25 minus 3, 22. And there is our simplified version. Does anybody recognize what pattern that is?
Final. Quadratic.
No.
First
First term squared minus the second term squared. It's a
perfect square.
not perfect square, but there's a subtraction in there.
Subtraction or addition.
Difference of perfect squares. Bravo. That's exactly what is happening here. This follows that same pattern. It's a difference of perfect squares. And so you know that those two center terms are always going to eliminate each other. So for this next one, I'm not going to FOIL it out and write out all those steps because I know the pattern. I recognize the pattern, so I'm just going to make this a little bit quicker. Okay, so again, there's nothing to combine here. I just have to get rid of that radical in the denominator. So I'm going to multiply by the radical conjugate, which is
6 plus the square root.
Can you not do anything to the 3 and the 6? Or...
So you have to remember, anything that simplifies, it has to go into every term.
There's another like implied negative one in front of the
Well,
So if it was like
if I had that,
it's multiplied, but when you
yes.
okay.
Yes, otherwise you have to apply it to every term. Okay, so here's our radical conjugate. Okay, so multiplying across the numerator.
Yeah. Since it's a radical conjugate, would we always, like, when we're doing this, always the middle numbers would cross out because it's negative?
Yeah, because, it's a difference of perfect squares. Okay, so 3 times 6 is 18. 3 times square root of 2 is positive 3 square root of 2. Alrighty. Remember, it's that same pattern, so I know I'm going to get 6 squared, which is 36, minus, we already know those two middle terms are going to disappear. Square root of 2 times square root of 2 is?
negative 2. Well, it's 4.
4. Square root of it, though, which is 2. Okay, and so in the end, I have 18 plus 3 square root of 2 all over 34.
Can you simplify?
Not
This one,
But if it was
yes.
but if it was like 33, you could take out 3's from all of them, right?
Yes,
Okay.
Yeah.
That's what
and we would.
okay.
Okay, ready for the next one?
Yeah.
Yay! Okay, C. I've got 7. 5th root of 12 minus 5th root of 12. Do we have like terms here?
Yes.
We do. Don't forget that even though there doesn't appear to be a value here, there is a 1 there. 7 minus 1 is 6. 6 5th root of 12. Is there any way to simplify the 5th root of 12?
No.
No. So that's it. Okay, what changed in D? It's in rational exponent form, not radical form, but is it the same thing?
Yes.
Yes. Okay, I still have in both cases a base of 9, and the exponent on both of those bases is the same. So are those considered to be like terms?
Yes.
Yes. All right, so we do 4 plus 8 is 12. And then we have 9 to the 2/3. And does 9 to the 2/3 simplify?
Yeah.
No.
Yes.
No. Yes.
Yeah.
Yes.
Yeah, because it's the same thing as having what the cube root of
Cube root of 2.
Which is
3 squared, 3 squared.
Wait, why is it 2 3 squared?
Because it's
Oh,
9.
never mind. I get that.
All right, so how many 3s am I going to, I have, basically I have 4 3s, so 1 can come out. So we get 12 times 3, and then we have the cube root of 3 left. 12 times 3, 36 times the cube root. Oh, wait, we started in what form?
Radical.
Exponent. So instead of having this, I want to change that 3 to the 1/3.
I have a question.
Yes.
Did the second 3 squared come from the 2 on top, like the 2/3, like the 2, because it's times 2?
Yes, because there's 2 9s.
Okay.
2 9s over here. So
Would
this,
we then do like 30 times 3 and then put 30
this is like doing 9 times 9. What was your question?
Would we then do 536 times 5 to the 1/3?
Okay, so remember that 3 to the 1/3 is a cube root of 3. So can you multiply those? Can you combine them? No, so it has to stay by itself. Okay. All right, so let's look at E. So first thing I notice is I have the same index, but the radicands are not the same. I cannot simplify the cube root of 5, but can we simplify the cube root of 40?
Yeah, I believe so.
Okay, so we keep the cube root of 5 because we can't do anything, but the cube root of 40, we can split that into
2 cube root 5.
yes, it's 8 times 5, so we're going to get a 2 out of that. So we have cube root of 5 plus 2 cube root of 5. Now do we have like terms?
Yes.
Yes. Don't forget the understood 1 here. So this is 1 plus 2, which is 3 cube root of 5. All right, we ready for F?
Yes.
Okay. So again, I'm going to look at this and I see that they're both 4th roots, but the radicands do not match. But can I simplify
Yes.
either of them? Yeah.
48 is 8 and 6. And then
Which is
go down
2
further, it's
times
2, 2, 2,
2,
Right.
2, and 3.
Okay. Multiple ways to go about it.
16 and 3 probably will work.
All right. Okay, so 16 is 2 to the 4th, so I'm going to get a 2 out of there. 4th root of 3 minus 4th root of 3. And do we now have like terms?
Yes.
Yes. Yep. Don't forget that understood 1 there. And 2 minus 1 is 1, so we don't have to put it. And all we need to put is the 4th root of 3. Okay. I feel like you guys got this down pretty well.
I agree.
Awesome.
Wait, what is the one called? Oh my god.
Which one?
There's more. There's more. I jumped out. It's so loud.
Understood 1? Yes. Yeah. It's understood. If there's nothing in front, it's just understood. Okay. All right. I have the square root of 9w to the 5th minus w square root of w cubed. Right. So again, I do notice that my indices, I should say, are the same for both of them, and both of these can be simplified. So that's where I want to start, is by simplifying both of them. Okay, so square root of 9 is 3. Square root of w to the 5th is
W squared.
w squared, and we're left over with a w.
Yes.
And for the second one, I have a w cubed,
So you can take out 2.
so I can get out 1 out. So then I'm going to have a w times a w squared, square root of w. Okay, so this one is a little bit different because not only do we have radicals in both terms, but there's also variables on the outside.
So you have to make sure that those are the same.
Those have to be the same as
They're
well.
both W squared.
They are. So since they're both w squared and we have the same exact radical, do we have like terms?
Yes.
We do.
So
Right.
if those two terms were different, would you not be able to do anything?
You would not be able to combine them.
Okay.
Right.
Thank you.
Okay, 3 minus 1 is 2. So we get 2w squared, square root of w. Okay.
Is H the last one?
Yes. Okay. And so keep in mind, let's say we had something more like 2a cubed square root of, we'll do 5, minus a squared square root of 5. Are those like terms? No, we could not combine them. Okay, so H is our last one, and then I've got much more fun problems for you guys to work on the board.
I have a question.
Yes.
For H, would you do like PEMDAS and do multiplication first, or could you add them?
No, you are right.
Okay.
So you would
Would you have to do the last two?
Oh, you have to do PEMDAS?
Yes.
It would have been so nice.
So 11 times 6 is 60.
Yes. Yes, we do.
Oh my gosh, I had already started.
Oh my god, was
And
anyone
I
here
did
to miss
as
a
a
class in
addition
first grade for
first.
math?
So this is going to become what?
7, just the regular 7.
Just the regular 7?
Wait,
No,
I don't know. You have to.
Would it be a 7 1/2?
Through?
I don't know.
Oh,
Oh, 6 over, wait,
I'm
this is 2/3.
when you're multiplying the 6, 7, 1/3 times the 11, 7, 1/3, do you have to distribute it to both?
It's not a distribution. There's no addition or subtraction in there. This is straightforward. 6 times 7 to the 1/3 times 11 times 7 to the 1/3.
Why is it that whole term?
But now you can't add them.
Now we can't add them.
Why is it 2 on the top?
I didn't catch that.
Okay,
Fifths or 2/3?
2/3.
Do you? Because you add the ones in the. I don't know.
Because the bases are the same. So when the bases are the same, when you're multiplying same base with exponents, what's the rule? Add them.
And you don't multiply the base together, like you don't do 7 times 7 is 49.
No, we just keep it like this.
Wait. Yeah, wait, that's what I got.
Hmm?
Oh, it's because it has the same base number.
Yeah. Yeah.
So that's why you can add them.
That's why, okay.
If it was like 6 2/3 and 7, or 6 1/3 and 7 1/3, you couldn't add them together, could you?
If you had what?
If it was in the parentheses, 6 to the 1/3 and the 7 to the 1/3, and 7 to the 1/3.
No, you can't combine.
Because you can't add them
Well,
together.
except that they're both to the 1/3, so actually you could put them under 1. You could do that.
Oh, okay.
Yeah, but you're not going to add the exponents. Yeah. So it just depends. Okay. As I said, I have much more fun problems for you guys to work on the board. Yep, that's the end.